Tamagawa numbers in the function field case. And we should be all set up to go, right? Okay.
All right. Thank you very much. So in this lecture, I would just like to go through a little bit of what the analog of Weil's conjecture would say in the case of a function field. So let me begin by reviewing what a function field is. So throughout this lecture, that's too big. That's the same size, never mind. FQ is going to denote a finite field with Q elements. And X is going to be an algebraic curve over FQ. When I say algebraic curve, I'm always going to mean it's smooth, projective, and geometrically connected, meaning that the ring of global functions on X is exactly FQ. And I'm going to write Kx for the fraction field of X. And so this fraction field determines the algebraic curve X up to isomorphism and vice versa. And so the data, a field which arises in this way is called a function field. And the data of a function field is really the same as the data of this bit of algebraic geometry, of an algebraic curve over a finite field. So there's a strong analogy between the behavior of number fields and the behavior of function fields. So let me just spell out some of that analogy. So on one side, let's say, on the left side we'll put number fields, and on the right side we'll put function fields. So a number field, by definition, is a field that appears as a finite extension of Q. So an example of a number field would be the rational numbers Q itself, and on the function field side, well, fields like the Kx that I mentioned earlier. So when you're working with the rational numbers, you're interested in things like prime numbers P. And the analog of that on the side of function fields is closed points of the algebraic curve. So I'll write little x in this lecture to always mean a closed point of the algebraic curve capital X. And, well, this maybe analogy is not quite perfect. Closed points of the curve maybe more properly correspond on the number field side either to prime numbers P or some point at infinity, corresponding to the Archimedean completion of the field of rational numbers. Now, if you have a prime number P, then you can form a finite field Z mod P. And that has an analog in the function field case to a closed point of the curve. You can associate what I'll write as kappa of X for the residue field of X at that point. So that's also a finite field. It's a field which is a finite extension of FQ. It has size q to the d for some integer d. Another thing which appeared in the previous lecture was the ring ZP of p-adic integers. That's something that you can associate to each prime number p. That also has an analog on the function field side. What I'm going to write, if you have a closed point of X, I'm going to write O sub X for the completed local ring. Of X, capital X, at the point little x. So this O sub X is a ring which is non-canonically isomorphic to a power series ring in one variable over the finite field kappa of X. So as soon as you choose a local coordinate at that point, this becomes a canonical isomorphism. So another object which appeared in the previous lecture was the field QP, p-adic rational numbers. That's the fraction field of ZP. That has an analog on the right-hand side, which I'm going to denote by k sub little x, and that's just the fraction field of O sub little x. So this is a field that you can associate to every point, and it just looks like you took the residue field at that point, and then a joined a Laurent series generator T. And maybe also in this case we have an analog corresponding to the Archimedean place. In the previous lecture I mentioned the ring of Adels, A. That has an analog on this side, which I'll write as A sub x, which is a restricted product of all of these local fields K sub x, where x ranges over the collection of closed points of my curve. So again, the restricted product means you consider the subset of the Cartesian product where all but finitely many of the components are required to lie in this subring O sub x. Okay, so this is a brief review of some general analogies. Now I'd like to get into some more specific analogies with objects that we were interested in the previous lecture. So before, in the previous lecture, we were studying quadratic forms. So let's say we could have a quadratic form, I'll write it as Q naught, over the rational numbers. And the analog of that in this lecture is going to be a semisimple algebraic group, which I'll call capital G0 over the field Kx. Maybe this would be more properly the analog of having a semisimple algebraic group over the rational numbers. Every quadratic form, non-degenerate at least, gives you a semisimple algebraic group by looking at the special orthogonal group of that quadratic form. So this is maybe a closer analogy here would be what I called in the previous lecture SOQ, or now Q0. Now in this situation, to this quadratic form Q0, we associated this adelic group, SOQ0 of the Adels. This was a locally compact group, and this has an analog on the function field side. You can take G0. It's an algebraic group over the field Kx. Therefore, you're allowed to take R-valued points where R is any Kx algebra. In particular, you can take its points with values in the ring of Adels, and that's a locally compact group. And well, inside here, we had a discrete subgroup, which was SOQ of the rational numbers. And inside here, we similarly have a discrete subgroup, which is G0 evaluated on the field Kx itself. What was important in our story this morning was that this locally compact group on the left had a canonical invariant measure on it called Tamagawa measure. And the construction of Tamagawa measure makes perfect sense in the function field case too. Any semisimple group over a function field, its adelic points have a canonical translation invariant measure, which is also called Tamagawa measure. And, well, Weil's conjecture, when I stated it for you, well, the nicest form of that conjecture was in the simply connected case. So let me say, for spin Q0 of the Adels, mod spin Q0 of Q, was that Tamagawa measure was equal to 1, and that has an analog on the right-hand side, which is the same statement. The Tamagawa measure of this quotient, G0 of AX, mod G0 of KX, should be equal to 1. So this is the statement that we got to at the end of this morning's lecture. So it's a sort of an abstract statement about volumes of adelic groups, but we got to it from a much more concrete statement about a counting problem, about counting quadratic forms within a genus. So that has an analog in the function field case too, but to state that analog, we need to fix a little bit more data. So on the number field side, we had a quadratic form not just with rational coefficients, but with integer coefficients. So let me continue this column of analogies. Q, a quadratic form over Z. And the analog of that in the picture that I'm going to describe is having not just an algebraic group defined over the field kx, not just having something defined at the generic point of your algebraic curve, but actually having a group scheme over X itself. So I'm going to denote that group scheme by G. So if you're not familiar with the language of group schemes, it means you have a family of algebraic groups parameterized by the algebraic curve X. And so an example that you could think about would be taking G to be X cross your favorite algebraic group, like GLN. That's maybe not such a great example because what's going to be important in a little while is the assumption that G is semisimple. Actually, I already made the assumption that G0 was semisimple. So this is actually not a great example because GLN is not a semisimple group, but you could fix that by taking something like SLN. And these examples, even though they might sound kind of trivial, they're perfectly interesting for everything that we're going to do. So if you ever have trouble thinking about a group scheme over an algebraic curve, just think of the group SLN, and everything will still be interesting. Okay, so what do you get when you have a group scheme rather than just an algebraic group defined at the generic point? Well, this algebraic group G0, you were allowed to evaluate it on any algebra over Kx. But a group scheme G, you can now evaluate on any commutative ring R for which you have a map from spec R into the algebraic curve X. So it makes sense to evaluate G on things like the residue field of capital X at some point, and that's the analog of objects that appeared earlier, like SOQ on, oh, well, maybe these objects didn't appear but explicitly, but they were sort of implicitly in the picture. Finite groups that you get by looking at symmetries of quadratic forms over finite fields. Okay, so now we started in the previous lecture with a counting problem. We wanted to count the number of quadratic forms in a genus. And remember, we counted with multiplicity. So we had this object that I called the mass of Q. It was a number which was given by 1 over the size of, well, what I said was OQ prime of Z, where Q prime is in the genus of Q. And there's an analog that we can write down on the right-hand side, which is also a sum, but now instead of a sum over quadratic forms, it's going to be a sum over principal G bundles. P on X, and the term is, again, 1 over the size of a symmetry group, 1 over the size of the automorphism group of P. So if you're not used to thinking about principal G bundles in general, a good example to think about is G is X cross GLN, and then principal G bundle just means a vector bundle of rank n. That's not a good example because GLN is not semisimple. If G is SLN, then principal G bundle means a vector bundle of rank n together with a trivialization of its determinant. So now let me warn you about something that's not analogous in this picture with the left-hand side. So something that I mentioned at the beginning of the previous lecture is that the sum that appears in the definition of the mass of Q is actually a finite sum. If you fix a quadratic form Q, then up to equivalence, there are only finitely many quadratic forms of the same genus. But in the setting that I'm going to be talking about in the function field case, that's not true. So this sum that appears over all principal G bundles is now an infinite sum. Up to isomorphism, there are infinitely many principal G bundles, but part of the story is the assertion that this sum is actually finite. Even though it involves infinitely many terms, as you start listing the G bundles out, you find that they have larger and larger symmetry groups, and that symmetry groups grow fast enough for this sum to be finite. Okay, so in the previous lecture, we arrived at the statement of Weil's conjecture from the Siegel mass formula, from a statement about the mass of Q. So let me just say on the left-hand side we had a mass formula, and on the right-hand side, similarly, the statement of Weil's conjecture in the function field case translates to something more concrete, now not about counting quadratic forms, it's about counting principal G bundles. So let's say over here we have the mass formula formulation of Weil's conjecture, which I'll just tell you what it works out to be. It's that this sum over isomorphism classes of principal G bundles, 1 over the size of the automorphism group of P. What does it work out to be? Well, Q is the size of my finite field, remember? Some power of Q times something that looks like an Euler product, a product over all the closed points of my curve of a certain fraction, namely you take the finite group G of kappa x and look at its size and divide that by your naive estimate for that size, which is the size of the fraction, the residue field kappa x raised to the power d, where here little d is the dimension of the group G. Or let's say the dimension of the group G0 as an algebraic group over the residue field case of x. So if G is a group of dimension d, then you would expect that if you took points of G with values in some finite field, the number of points would be roughly the size of the field raised to the power d. So the factors that appear in this expression are numbers that you would expect to be reasonably close to 1. And so this is a product that you might hope converges. And the statement of Weil's conjecture is that, in fact, it does converge, and it converges to something which has an interpretation in terms of counting G bundles on X.
Jacob, could you say with the cube the D, what's that capital D?
That capital D is an integer, which I will tell you about in a little bit. Yeah. Okay, so this is what you would get if you just ran the previous lecture in reverse. You'd arrive at this statement as a reformulation of Weil's conjecture. So this is supposed to be easy, right? Weil's conjecture over Q is a statement about number fields, so you expect it to be hard to prove. This is a statement about function fields. It's supposed to be easy to prove. And specifically, what we're supposed to be able to do is take advantage of the connection of function fields with algebraic geometry. So how does that play out in this case? Well, in the case of number fields, we were trying to count the number of quadratic forms in a genus, and that didn't have a lot of structure to it. The quadratic forms in the genus of Q, they just formed some set. But in this lecture, we're trying to count principal G bundles on an algebraic curve. And in that case, there's a lot more structure because the principal G bundles are parametrized by an algebrogeometric object themselves. So let me introduce an object, which I'm going to denote by bun_Gx. This is called the moduli stack of G bundles. So what is it? Well, it lives in the world of algebraic geometry, and it has the following, it's defined by the following property, that to give an R-valued point of bun_Gx, so maps from spec R into bun_Gx are the same data as giving principal G bundles on X cross spec R. And here, I'm imagining that all my algebraic geometry is happening over the finite field FQ. So in other words, we can talk not just about a principal G bundle on X, but a family of principal G bundles on X parametrized by some other scheme or algebraic variety or something like that. So I'm using the word stack here. This is an algebraic stack, which means that when I talk about its R-valued points, that's not something you should think of as a set. That's something that you should think of as a groupoid, or as a category in which all the morphisms are isomorphisms. We want to talk about not just about G-bundles on X and their isomorphism classes of G-bundles. We want to know about automorphisms of G-bundles on X. We don't want to just view the G-bundles as forming a set. But if you're not familiar with the language of algebraic stacks, again, if imagine every time I write stack, I was writing the word variety, you won't miss too much. This object is not just a stack, it's what's called an algebraic stack, which means that it's not too far from being an algebraic variety. And so our goal is to prove some equality of numbers, but let's say it's to compute the number that appears on the left-hand side. We would like to compute what I'm calling the sum of, the sum over all principal G-bundles of 1 over the size of the symmetry group. And what I want you to think of, a principal G-bundle on X itself is an FQ-valued point of this moduli stack bun GX. And if you ignore these denominators, then what I'm just asking for is the number of FQ-valued points on bun GX. But what I'm literally asking for is not the number, but the number counted with multiplicity, where the multiplicities have to do with these finite symmetry groups. So I'm going to write bun GX FQ, or absolute value signs around it, to mean that you're measuring the size counted with multiplicity. In other words, that's just a name for what appears on the left-hand side. And we would like to say something about this. Well, let's imagine that we weren't talking about a stack, but we were just talking about an algebraic variety. So let's go on a little digression. So let's say Y is an algebraic variety over a finite field FQ. Then you can look at the FQ valued points of Y, and that's some finite set. And you can ask, how big is that finite set? And this is a very subject of another very beautiful idea of André Weil. So let me describe Weil's idea for how to count a set like this. So the idea is to think of, well, first let's let Y bar be the same variety, but viewed not over a finite field, but over its algebraic closure. And now the idea is to think of Y of FQ, this finite set, as sitting inside this algebraic variety, Y bar, over an algebraically closed field. And in fact, it sits inside there in a very specific way. There's a map from Y bar to itself, using the fact that Y bar is actually defined over a field with Q elements. There's a canonical map of algebraic varieties from Y bar to itself called the geometric Frobenius map, which is just given if I think of Y bar as sitting inside some projective space, say. It's just given by restricting a map from projective space to itself, which in homogeneous coordinates takes x0 through xn to x0 to the q xn to the q. So for Y bar is defined by inside of projective space as the solutions to some polynomial equations where the coefficients are in FQ, then raising everything to the qth power is an operation that takes a solution to those equations and outputs another one. So this phi gives you a map from Y bar to itself, and then the FQ valued points of Y are just the fixed points of this geometric Frobenius. And so Weil's idea is that if you're trying to count the number of fixed points of this map, then you ought to be able to do this by some version of the Lefschetz fixed point formula. So the number of FQ valued points of Y should be something like an alternating sum of the trace of this Frobenius map on the cohomology groups of this variety Y bar. And, well, this is what it should be if when Y is a projective variety. If Y is only a quasi-projective variety, then I should take some kind of compactly supported cohomology here. So when Weil was thinking about this, it was a heuristic. And it was a heuristic that he used to make a number of predictions about the behavior of these numbers of points of algebraic varieties defined over finite fields. And these were tremendously influential in algebraic geometry. And these conjectures that Weil made were eventually turned into theorems by Grothendieck and his students. And the way that they proved these theorems was by actually making sense of these cohomology groups. So here, Y and Y bar, Y is defined over a finite field, Y bar is defined over a field of characteristic P. They don't have reasonable topological spaces in the usual sense to which you can apply the usual constructions like cohomology and homotopy. But what Grothendieck and his students did is introduce adequate replacements for those notions, which make sense for schemes in general. And so, this is now, so this idea that this should be equal, this is now a theorem called the Grothendieck-Lefschetz trace formula, or I guess in this case, the Grothendieck-Lefschetz fixed point formula. And to turn it into a theorem, well, you have to say what you mean by these cohomology groups, and these cohomology groups are given by the L-adic cohomology of Y bar, where L is now some prime number which is not equal to 0 in the finite field FQ. Okay, so the idea that I would like to pursue is applying something like this Grothendieck-Lefschetz fixed point formula not to an algebraic variety over FQ, but to an algebraic stack like the moduli stack of G bundles. But before I do that, I would actually like to reformulate the Grothendieck-Lefschetz fixed point formula. I'd like to state it in a slightly different way. So I'd like to not appeal to the theory of compactly supported cohomology. So as a replacement, let me assume that Y is smooth. Of dimension D. And, well, L-adic cohomology has the feature that it satisfies Poincare duality for smooth varieties. So what this implies in particular is that if you look at the compactly supported cohomology of Y bar, well, in some degree I, that this is canonically dual to the cohomology in degree 2D minus I. Y. So this is some form of Poincare duality. Y bar, thank you. And let me warn you, I just said the word canonical, but that's a little bit wrong because, well, it actually depends on something that plays the role of an orientation of Y bar. And that choice of orientation cannot be made in a Frobenius equivariant way. So this isomorphism, I should say, is not phi equivariant. So you should think of this isomorphism as coming from the fundamental class of Y bar. And the geometric Frobenius map, it involves raising all the coordinates to the qth power. It's not a map of degree 1. It behaves like a map of degree q to the d. So the upshot of this is that another way of writing, if you want the trace of Frobenius on the compactly supported cohomology of Y, another way of getting that is to take the sum of the trace of the inverse of the Frobenius map on the cohomology groups of Y bar. But what you get when you do that is not the size of y of fq, it's instead a sort of normalized version of the size of y of fq. It's the size of y of fq divided by q to the d. So here, y is an algebraic variety of dimension d. Your back of the envelope estimate for how many points, how many elements should the set y of fq have, well, it should be the size of the field raised to the power d. So this is a number that you would expect to be close to 1, and an equivalent form of the Grothendieck-Lefschetz trace formula is telling you exactly how close it is. So it's given by this alternating sum where the I equals 0 term is the number 1, and the other terms are some corrections. Okay, so now the idea is that we would like to apply this to when y is this algebraic stack that I called bungee x. And so what would it mean? So definition, bungee x satisfies the Grothendieck-Lefschetz trace formula if, well, it should tell us something about the number of points of bungee x over fq, but now I mean number of points interpreted in the earlier sense. I'm counting points with multiplicity. So this, I should see a sum over all principal G bundles of 1 over the size of that automorphism group. And, well, if I'm writing the analog of this Poincare dual form of the Grothendieck-Lefschetz trace formula, I should then divide that by q to the dimension of bungee x. And the Grothendieck-Lefschetz trace formula would say that this should be something like the sum, the alternating sum of the trace of the inverse Frobenius on the ith cohomology of bungee x. And I'll put a bar on that to mean that I'm really thinking of that over the algebraic closure of fq rather than fq itself. So I'm going to be writing these alternating sums over and over again, and from now on I'm just going to call this the trace of Frobenius inverse on the graded vector space given by h star bungee x. Okay, now I can answer the question, what's D? Remember, I said if you think about what the mass formula translates, or sorry, what the Weis conjecture translates to concretely in terms of a mass formula, it was telling you that 1 over the size of some automorphism group should be a certain power of q times something. That power of q that appears, it's the dimension of bungee x as an algebraic stack. So this, well, capital D is the dimension of bungee x. And therefore, if you wanted to prove Weis conjecture, you could try to do it in 2 steps. So Weis conjecture follows from 2 pieces, or 2 lemmas, 2 assertions. The first is that the Grothendieck-Lefschetz trace formula is actually okay in this context. So part 1 is bungee x satisfies the Grothendieck-Lefschetz trace formula. So that will tell you that if you take this mass and divide it by the power q to the d, that this should be something which has an interpretation in terms of L-adic cohomology. This should be the trace of Frobenius inverse on the cohomology of this bun Gx. And the second is that this trace is equal to the thing that we want it to be, something with an Euler product expansion. This is something which is a product over the points of the curve of, well, I wrote it perhaps illegibly earlier, but a product of local factors where each local factor is, the numerator is the size of g of kappa x, and the denominator is your naive estimate for that size, the size of kappa x itself raised to the power equal to the dimension of the group G. Okay, so let me first comment on the first part, because I'm not going to say anything else about it in this series of lectures. So, first part, let's just say, I think the first place where this was proven in some cases is the thesis of Kai-Behrendt. So this is a theorem of Behrendt in the case where G is a constant group. Or I think more generally, in the case where G is a group which is everywhere semisimple. Now, that's something that you can't always arrange in this picture. So G, I should have mentioned earlier, I'm making some assumptions about the group scheme G in this story. So the generic fiber of G, that's my algebraic group G0, I told you should be semisimple and simply connected. But in general, if you think of G as a family of algebraic groups, you can't arrange that every single member of that family is also semisimple and simply connected. You can arrange that every member of that family is a smooth affine group, but it's unavoidable that at finitely many points that group might fail to be semisimple. And so, well, let me just say this was generalized. You can find a proof in my book with Dennis Gaitsgory, which came out, I think, last month. This Kai-Behrendt's argument can be generalized to the setting where G is one of the group schemes that we're interested in, where it might have bad reduction at finitely many points. But the proof that we give of this is not so great. And that's actually the subject of the problem set that I gave. That it should be possible to give a better proof of that statement, which is closer to what Kai-Behrendt's does in the case where G is a nice group. And but it requires you to have something like the Harder-Narasimhan stratification for more complicated kinds of groups. So let me not say anything more about that in this lecture series, because the theme of the winter school this year is interactions between number theory, arithmetic, and algebraic topology. And this second step is really where the new ideas come in. So I'm going to elaborate on those new ideas in my other lectures, but let me just start with a really vague description of why you might expect something like this to be true. How long do I have, by the way? I haven't heard the thing go off yet.
11 minutes.
Oh, I have a ton of time. So actually, let me say a little more about these Euler factors that appear in the right-hand side. So let me go on a little digression. So let X be a closed point of my curve capital X. So then I can look not just at G bundles on my entire curve, I can also look at G bundles that are defined just at that one point of the curve. So there's a moduli stack of these. Another name for this moduli stack is, it's the classifying stack of the group that I get by taking the fiber at the point X. And so now this is a pretty simple looking stack. So there's a theorem of Lang. Well, so let's say we were interested in taking the FQ points of this. In other words, we were interested in counting the number of G bundles not defined on the entire curve, but just defined at that one point. So this This is the category of principal G bundles. On just the affine scheme, which is the spectrum of the finite field kappa x. Now, there's a theorem of Lang that says that as long as the fibers of G are connected, that this category of principal G bundles has only one object, that every principal G bundle over a finite field is automatically trivial. So this category has one object up to isomorphism, but that object has some symmetries. It's the trivial G bundle, so its symmetry group is exactly the group G of kappa x. So then if I asked, what's the number of principal G bundles at the point x counted with multiplicity? Well, that would be 1 over the size of this finite group G of kappa x. So that's the number of points, but what if I was to normalize that by dividing by the expected number? So let's divide on the left-hand side by the power of q to the dimension of bun-g x, bun-g little x. Well, that dimension is just the degree of the point x times minus the dimension of the group G itself. So actually dividing by this power of q, what it really amounts to is multiplying, putting something in the numerator, which is the size of kappa x raised to the power d. So these are the local factors that appear in the mass formula formulation of Weil's conjecture. So let me mention, if you look at these bun-g x's, these also satisfy the Grothendieck-Lefschetz trace formula. That's something that I'm going to expand on in the next lecture. It's not a hard thing to prove. It's essentially equivalent to a formula of Steinberg for the size of a finite group of Lie type. So what does this tell you? Well, it tells you that this expression that appears here on the left-hand side, the number of FQ valued points divided by Q to the dimension, that I said is kappa x to the d divided by the size G of kappa x. That's equal to, oh, sorry, I wrote this wrong. I think I wrote that wrong everywhere. This should be equal to the trace. Yeah. This should be equal to the trace of Frobenius on the L-adic cohomology of this, let's say, bun-g little x. I'll put a bar on it to mean you have to go to the algebraic closure before you take that cohomology. And so then what Weil's conjecture is saying has a statement that you can make just purely about L-adic cohomology. And the idea is that the trace of the inverse Frobenius on the cohomology of bun-g of your entire curve should factor as a product over all the closed points of your curve of the trace of Frobenius on the cohomology of the moduli stack of G bundles, which are defined just at that point. Now, why would you expect something like this to be true? So let me put a question mark next to this. Once you know that everything satisfies the Grothendieck-Lefschetz trace formula, this is what Weil's conjecture is saying. Now, why would you expect something like this to be true? So when I first learned what a vector bundle was, it was explained to me heuristically like this. To give a vector bundle on a space, you give a vector space you assign a vector space to every point of the space, and those vector spaces should vary continuously from point to point. So that's some rough picture of what a vector bundle is. And similarly, what's a principal G bundle on a space? It means a family. You give a principal G bundle at each point, and they should somehow vary continuously. So let me write that in a rough heuristic form. Bun Gx, this space which parameterizes G bundles on your entire curve, is like a product over all the points of X of bun G at that point. And well, it's in quotation marks. This should be some kind of continuous product. It's really just a heuristic. But now if X was not an algebraic curve, but it was a finite set, then this would be literally true. The algebraic stack on the left would factor as a product of the algebraic stacks that appear on the right. And in that case, you would be able to describe the cohomology of the stack on the left by some kind of Kunneth formula. So let's imagine that you had a Kunneth formula for these kind of continuous products. And then it ought to say something like the cohomology of bun Gx, again, everything over the algebraic closure, should be something like a continuous tensor product over the points of X of the cohomologies of these bun Gx at the individual points. And now the idea that Dennis and I implemented to prove this equality over here was that you can actually make sense of this. So this statement makes sense, well, maybe not quite as I wrote it, but you can make sense of it using some version of the theory of factorization homology. Well, what do I mean by that? Well, the left-hand side is something that's well-defined if you know about L-adic cohomology on stacks. And the right-hand side is something that's in quotation marks. It should be some kind of continuous tensor product of L-adic cohomology groups of indexed by an algebraic variety. So the first challenge is to make sense of what you mean by the right-hand side. And the second challenge is to show that once you make sense of it, it actually computes for you the left-hand side. And provided that you can do both of those things, well, then you ought to be able to extract an equality of numbers by taking the trace of Frobenius on both sides. So that's where we'll pick up from next time. Thank you very much.
All right, any questions?
Yeah.
You mentioned that this is an unusual situation where the function field case is harder than the number field case?
Well, I don't know if it's harder, but it was something that was proven for number fields before it was proven for function fields.
Are there other examples that you know of where that's happened?
I don't know, but I'm not a number theorist, so.
In the infinite product over all the little x's of the mass of the bungee of the little x, are like most of those numbers the same?
Most of the, no, they, but they're similar looking. Like they, the sizes of the finite fields that appear are different. So you wouldn't expect them to be the same. I mean, it's more like, I think an example of one of the products that will come up is something like a product over all x in x of 1 over 1 minus 1 over the size of this squared. So it's, what's the number of points of SL2 of FQ? Right, this is something like the size of this group is q cubed minus q, I think. And so if you divide by q to the dimension, you get q cubed minus q divided by q cubed. So 1 minus 1 over q squared. And so the kind of infinite product that you see here, a rough model for it, it's like a product of a bunch of factors like this, but it's not the same number q that appears. It's at at each point x, you replace q by the size of kappa x.
So I suppose this is analogous to the appearance of the zeta functions in the number field.
Yeah, and in a later lecture, I will say it exactly that way.
So in the number field case, the mass formula was for a specific genus. In the function field case, it was all principal G bundles. What's the distinction here?
Well, once you fix what G is, you've sort of said, like to say that a quadratic form is in a genus is to say that locally it looks like a specific thing. And a principal G bundle is by definition something that locally looks like G itself. So you should think of choosing your quadratic form as, well, as I said, analogous to fixing the group G, and then.
Great, thanks.
Further questions?
Is there an example of an algebraic stack that doesn't satisfy growth and Lefschetz formula?
Yeah, so an example would be, what if I took bun G, but I took G to be the multiplicative group? So then bun Gx is classifying line bundles on X, and it looks like a disjoint union over all integers of bun Gx, where you fix the degree of your line bundle to be that integer. And so this does not satisfy the growth and Lefschetz trace formula for the stupid reason that like every expression that appears there will diverge. You won't be able to count the number of points because, or maybe it does satisfy it because the formula becomes infinity equals infinity. But this is the kind of thing that you have to worry is not happening in order to prove that bun Gx satisfies the growth and Lefschetz trace formula in the semi-simple case.
Well, I guess this is again analogous to something you said in the number field case. This is like why you passed from O to SO.
Exactly, yeah.
If you look at the smooth covering of the bun G, I think it emits a smooth covering by scheme. So if you look at the sort of the growth and trace formula for the scheme and the growth and trace formula for the stack, is there like a relation?
Yeah, so I mentioned that this is a theorem of Kai-Berendt that the growth and Lefschetz trace formula is true for bun G. So it does not follow formally that that's true from knowing it in the case of schemes, but the problem is not really that bun G is a stack. The problem is that bun G is not quasi-compact, right? That you're trying to say something about this, where'd it go? About this sum. And this is really an infinite sum, so you have to prove that something converges. And if you restrict to any quasi-compact substack of bun G, it becomes a finite sum, and you can deduce the trace formula from knowing that it's true for algebraic varieties.
Okay. Any last questions? Maybe take one more. I guess I'll just.
For semi-simple G, which are not simply connected, what breaks down in the story?
So for semi-simple G, which are not simply connected, this product formula, if G is not simply connected, then bun Gx is not connected. And roughly this product formula for the cohomology, like replacing G by its simply connected cover, is not going to change. Where did I state the heuristic? Right, so there's some, where'd it go? Here it is. So there's some heuristic formula, or you can make it precise using the language of factorization homology, that you recover the cohomology of bun Gx as some kind of continuous tensor product of these local factors. Replacing G by its simply connected cover doesn't change these local factors. You're computing cohomology with rational coefficients. But it does change the cohomology of bun Gx itself because bun G acquires some new connected components. So this formula will be wrong roughly because it's forgetting about the non-identity components of bun G.
Okay, if there are further questions, maybe we can go ahead and take those offline. Let's thank Jacob again. And one more time, the